Let us consider example 1. Steam as a saturated vapor enters our turbine at a pressure of 8 MPa, and saturated liquid exits our condenser at 8 kPa. If the net power produced is 100 megawatts, we want to determine the thermal efficiency of the Rankine cycle, the back work ratio, the mass flow rate of the steam, the rate of heat supplied to the boiler, and the rate of heat rejected from the condenser. For us to begin, we are going to list our state variables. Recall state 1 is the input into our pump. Our pressure at state 1 is 8 kPa, the same pressure as the steam entering our condenser. Our quality at state 1 is 0. At state 2, our pressure is increased to 8 MPa. That is, at state 2, our fluid is exiting our pump and entering our boiler. At state 3, we have a pressure at 8 MPa and a quality of unity. This is where our fluid enters our turbine. And at state 4, the exhaust of the turbine is entering the condenser. For us to determine the thermal efficiency, which is our net power per heat input, we want to express this in terms of our enthalpies. Our thermal efficiency, which is the work of the turbine, less the work of the absolute value of our pump per the heat supplied to our boiler, is the mass flow rate of our working fluid times H3 less H4, that is the work done by our turbine, less the absolute value of our mass flow rate times the difference of H2 less H1, which is our pump work, per our mass flow rate times the differences of our enthalpy at the exit and inlet of our boiler, H3 less H2. Our mass flow rates drop out, thus our thermal efficiency is expressed as H3 less H4 less the absolute value of H2 less H1 per H3 minus H2. Starting sequentially, we need to find our enthalpy at state 1. We're given a pressure of 8 kPa and a quality of 0. Thus, if we use our saturated liquid pressure tables, referencing our saturated liquid specific enthalpy, we can determine our enthalpy at state 1, being that of our saturated liquid specific enthalpy taken at 8 kPa, which is 173.378. To determine our enthalpy at state 2, we're going to need our entropy at state 2, because we're assuming we have a constant entropy process within our pump. To determine our entropy at state 2, we need our entropy at state 1. And this is found via interpolation between our 7.5 and 10 kPa pressure entry tables, where we interpolate between our specific entropy. Thus, S1 is equal to our saturated liquid specific entropy taken at 8 kPa, which is found to be 0.59088 kJ per kgK. Next, the enthalpy at state 2 is found via our pressure and our entropy. If we construct an intermediate pressure entry table for compressed liquid water, we have a 5 MPa and a 10 MPa entry. The pressure of our fluid entering our boiler is at 8 MPa. Our entropy at state 2 is the same as state 1, or 0.59088 kJ per kgK. We can interpolate for our enthalpy at state 2. That is, our enthalpy at state 2 is found to be 181.621 kJ per kg. Alternatively, we can recall that our pump work per our mass flow basis is equal to the difference of our enthalpies. Our enthalpy is the difference of our internal energy plus our specific volumes times our difference of pressures. Since this is a compressed subcooled liquid, our specific volume between state 1 and state 2 does not change, and our internal energy between state 1 and state 2 is assumed 0, for our internal energy is strongly a function of temperature. Thus, if we determine our specific volume at state 1, we can use the difference of pressures between state 2 and state 1 in our already given specific enthalpy value at state 1 to determine our enthalpy at state 2. Our specific volume at state 1 is found via interpolation using our saturated water pressure tables of our 7.5 and 10 kPa entries. Thus, our specific volume at state 1 is found to be 0.0010084 meters cubed per kg. Thus, our enthalpy at state 2 is equal to H1 plus nu1 times the difference of P2 less P1. Or our enthalpy at state 2 is found to be 173.378 kJ per kg plus 0.0010084 meters cubed per kg times the difference of 8,008 kPa. Or our enthalpy at state 2 is equal to 181.437 kJ per kg, which is very close to the enthalpy we found via using entropy. The enthalpy at state 3 is found directly from the table. We are given a pressure and a quality. Thus, H3 is equal to our saturated vapor taken at 8,000 kPa, or 2,757.94 kJ per kg. Our specific entropy at state 3 is found as our saturated vapor specific entropy taken at 8,000 kPa, which is 5.7431 kJ per kgK. Now, the enthalpy at state 4 can be found based upon quality and the fact that our entropy at state 4 is equal to our entropy at state 3. That is, we are assuming our turbine is a constant entropy device. Noting that our saturated liquid specific enthalpy evaluated at 8 kPa is equal to that of our enthalpy at state 1, we can interpolate to find Hg and Sg at 8 kPa. Our saturated vapor specific enthalpy at 8 kPa is found to be 2576.63 kilojoule per kg. And our saturated vapor specific entropy at 8 kPa is found to be 8.23114 kilojoule per kg K. Now we can use the definition of quality to relate entropy and enthalpy. Our quality at state 4, which is equal to S4 minus SF per Sg minus FF, is equal to H4 minus HF per Hg minus HF. Or our enthalpy at state 4 is given as 5.7431 minus 0.59088 kilojoule per kg K per 8.23114 minus 0.59088 kilojoule per kg K times the quantity 2576.63 minus 173.38 kilojoule per kg plus 173.38 kilojoule per kg. Or our enthalpy at state 4 is found to be 1794.01 kilojoule per kg. Thus, with all our enthalpy values known, we can evaluate our thermal efficiency as follows. We have H3, which is 2757.94, less H4, which is 1794.01, less H2, which is 181.437, plus H1, which is 173.378, per H3, which is 2757.94, less H2, which is 181.437. Or the thermal efficiency of this particular Rankine cycle is 37.1%. Now we can calculate the back work ratio, that is the pump work per the turbine work. Our back work ratio is H2 less H1 per H3 less H4. And we find our back work ratio to be 8.36 e to minus 3. We want our pump work to be substantially less than our turbine work. Otherwise, our power plant is consuming much more energy to continually run. Now, the mass flow rate of the steam can be found by using our net power output. Our net power output is the work of our turbine less our work of our pump, and this was equal to 100 megawatts. Now, the net work is our mass flow rate times the quantity H3 less H4, which is our turbine work, less H2 less H1, which is our pump work, and this has to be equal to 100 megawatts. Or our mass flow can be 100 e to the third kilowatts per H3 less H4 less H2 less H1. Thus, our mass flow rate for this particular cycle to execute based upon our given state variables and our net power output has to be 104.57 kilograms per second. The heat supplied to the boiler is simply our mass flow rate times the difference of our enthalpies at state 3 and state 2. That is 104.57 kilograms per second times 2757.94 minus 181.437 kilojoule per kg, which gives us 269.43 megawatts. We note that the heat supplied to our boiler is drastically larger than the work out from our turbine. This makes sense. For a heat engine, our net work cannot be identically equal to our heat supplied. We have to communicate with a low temperature reservoir. And the heat rejected to this low temperature reservoir, i.e. from the condenser, is found via our mass flow rate times the difference of enthalpies at state 4 and state 1. Thus, our heat rejected from our condenser is 104.57 kilograms per second times 1794.01 minus 173.378 kilojoule per kg, or we're rejecting 169.5 megawatts.